Hello. Let's try some sample diploma board questions from Lens Stuff. So in an investigation, a group of students measures an object to be 10 centimeters tall. They place an object 3.2 centimeters in front of a thin lens. They observe a virtual image. Okay, so that's a key piece of information. It's virtual, is formed. They measure the distance to the image to be 4.3. So the type of lens and its calculated focal length are cool. So let's do this. So we have hi-ho, dido, and focal length. So the object is 10 centimeters tall. And they place the object 3.2 centimeters from a thin lens. They observe a virtual image, so the distance to the image is going to be negative. A virtual image is formed and they measure the distance to the image to be 4.3. Okay, so that negative is really important in there. A lot of people would forget that negative and then end up getting this question wrong because they don't put it in there. So all we have to do for this is 1 over f equals 1 over di plus 1 over do. But if you don't put that negative in there, then you end up getting the wrong answer. So 1 over negative 4.3 plus 1 over 3.2. And then 1 overing that, so negative 4.3 plus 3.2, and we end up getting positive 12.5 centimeters. So that positive tells us that it's converging, and it's a lens, so that's going to be convex. So that's what we need to do the answer. So it's going to be 13 and it's going to be converging. So D is the correct answer. An object is placed 35 centimeters from a diverging lens. So already I see diverging, and I memorized diverging is always going to be smaller, virtual, and erect. So D, there we go. D is the correct answer. Easy. Don't have to do calculations with that one. Okay, this question here is our lab. So that's the lab that we did, and this is the ruler. We need a screen, we need a light source like a candle, and we need a lens or a mirror. So it's saying students use 3 of the optical apparatus illustrated to produce a focused real image in a darkened room. So one of the apparatus has a focal length of 10 centimeters. The student places one apparatus at each of the location on the optics bench as shown below. The optics bench is scaled in millimeters and labeled in centimeters. Okay, so we have to set up our experiment. So we can set up a lens or a mirror. So we don't want a diverging lens. So this one's out. We're going to use a candle. You can use a laser pointer, but a candle works a little bit better. We haven't learned this. This one's out. We haven't learned this. So this one's out, and we don't want a flat mirror. So these are the possible things that we can use. So if we're using a lens, we'd set our candle up here. So that's our candle right there. And we'd have to put our lens here. And we'd have to put our screen here. So that would be a possible situation if we're doing a lens, but we have to actually check if we get the right answer. And this is a super tough question. So here we have a distance of 15 centimeters. So that's our do. And then this looks like 10, 11, 12, 13, 14, 15. Yeah. Di ends up being 15 centimeters as well. But we have to see if that gets us a focal length at 10. And if it's not a focal length at 10, then we're going to have to use mirrors. So let's check that out. So both die and doe are 15 centimeters. So if we go 1 over f equals 1 over die plus 1 over doe, we end up getting 1 over 15 plus 1 over 15 and 1 over, and see if that gives us a focal length of 10. And it doesn't. It gives us a focal length of 7.5 centimeters, which means that what we drew there, we can't use a lens, we have to use a mirror. We didn't use a mirror in the lab because it doesn't work very well in real life. It's really hard to set up. But if you, I'm just going to clear all the ink from this. If you set up a mirror, what you need to do is, so you have your candle here, and then you have your mirror here, and we want to produce a real image, right? So that means that our screen would have to be over here. And I know it's like, well, won't the screen block it? But you just kind of offset it a little bit. I'll show you what I mean by offsetting it. So if this was our mirror here, right? And then this was our screen here, right? You think it would block the candle. Let's say, oops, this is my candle here. But you wouldn't do that. You'd offset the mirror and the screen a little bit like that, and it just doesn't work very well in real life. It's hard to get a nice focused image, but you'd sort of do it like that. Or you could put it slightly above like that and then angle the mirror upwards like that. So it doesn't block the image, so you don't have to worry about that. I always get lots of questions about that. So we always measure it from our mirror. So this would be the distance to our object, which looks like it starts at 5, ends at 35. So that's going to be 30 centimeters. Yeah, just double checking that. And then the distance to our image is going to be this. So die ends up being 15 centimeters. Okay, so we'll switch that up. So die is 15 centimeters and doe is 30 centimeters. So now if we plug that into our equation, so the only thing that we're changing is we're making this 30. So we go 1 over 30 plus 1 over 15, and then 1 over that, and then we get our focal length to be 10 centimeters when we do that. Okay, super tricky question. I wouldn't put this exact one on a test because I think a lot of people get it wrong. So our candle looks like it's at X, so our candle is 1, and then our screen is at location Y, so that's 9, and then our mirror that looks like this is at location 4, so 194 would be the correct answer. Okay, yeah, tough question. Hopefully that I explained that good enough. Okay, so today we're going to do the Young's double slit experiment. Tomorrow I'll set up a little lab very similar to the last lesson on it, so you can sort of see what this looks like in real life, because it's hard to just like do the calculations and not see what this is actually doing. Okay, so curriculum points. Describe qualitatively how Young's double slit is wave model. So all this stuff we're doing now is wave model. Use these equations, and then we can only use one equation in one situation. So we'll talk about what that means. So that's what this is saying, is that you can only use it for angles less than 10 degrees. So it won't make much sense if I talk about it now. And also describe diffraction and interference, predict the conditions required for diffraction to be observed, and demonstrate the relationship among wavelength, slit separation, and screen distance. And then observe visible spectra by diffraction grating. So that's all that we're going to cover in this lesson. Okay. So diffraction is something that we did in Physics 20. Diffraction is the spreading out of waves as they go through an opening or around a corner. Bigger wavelengths diffract better. So which color of light is going to diffract the best? Well, you have to remember that red is 700 nanometers. So this is red, and then blue is 400 nanometers, right? So red is going to diffract the best because it's a bigger wavelength. 700 is bigger than 400. Okay, and if you have a smaller opening, it increases diffraction as well. So to show you what diffraction looks like, if I send a wave through this, what diffraction will do is it'll bend around the corner there, right? And I talked about this in sound. If I'm here and I'm speaking through the doorway, if someone is over here, they'll be able to hear it because those sound waves bend around that corner, right? So this is a wave, and that's what it does, right? A particle doesn't do the same thing. So let's say I took a paintball gun, and I shot a paintball gun through there, right? And we had a screen on the other side. What I'm going to see on that screen is I'm going to see paintballs on the wall, but only where the size of the opening, right? That's what happens with particles. But a wave, because they diffract and they bend around that corner, we don't get the same pattern on that screen. What we get is we'd still get like the loudest sound, the most waves through that opening, but we'd also get waves hitting the wall around the side, right? So this is what it would look like for a wave on the screen. So the thickness of the line just represents how many waves hit that. So it's still thickest in the middle, but it still bends around the sides. But with particles, you just get it through that opening. Now, if we increase the size of that opening and we send some waves through this, we're not going to get as good a diffraction. What's going to happen is that these waves are still going to bend a little bit like that, but they don't bend all the way around the corner. So if I had a screen on this side, I would still get my biggest concentration through that opening, but I wouldn't get as much diffraction. It would still get a little bit on the sides, but not as far as the smaller opening had, right? And then if I do the same thing with waves, so I send my paintball through the opening, right? And I have a screen on the other side. I'm going to get my paintballs detected through the opening here, but I'm not going to get any diffraction. And you can see that when we make this opening bigger, waves and particles, the pattern that we get is very similar, but if we make it a very tiny opening, we get very different patterns on that wall. Okay, so that's what diffraction is. That's what you need to know. Interference, there's two types. There's constructive interference, and then that's where waves meet in phase and they amplify each other. So you can see that a crest matches up with a crest and a trough matches up with a trough. And by amplify, we get bigger amplitude. So instead of having 1A as our amplitude, we now have 2A as our amplitude. Okay, destructive interference is where they meet out of phase, they cancel out. So now we have a crest meeting up with the trough meeting up with a crest, and if we have positive A and negative A, we end up getting nothing left over. Okay, so they end up canceling each other out. So when light goes through an opening, you get a beam of light. Is this light acting more as a wave or more as a particle? So here I have my picture, right? The beam of light is going through, and we can see that the beam of light that goes through kind of just looks like the paintball situation, right? We only get the light the size of the opening. We don't get that light sort of bending around the corners there. So it looks like it's behaving more as a particle. And Newton, who said that light was a particle, this is one of his biggest arguments, right? He said that we didn't see light diffracting, and that's what waves do, so light must be a particle. So why don't we see light diffracting around objects? And the reason is because the wavelength of light is so small, right? The biggest wavelength of light that we can see is red light, and red light is 700 nanometers. So to get it diffract good, you need to have an opening that's less than that. You need it to be smaller than the wavelength. So that's why we don't see it. So until they had like good blades, like surgical blades to make openings and things, we couldn't really see light diffracting very well. So the reason light doesn't normally diffract is the wavelength is so small. Visible light's 400 to 700 nanometers, but light can be made to diffract through very thin slits for light to pass through or around. So the first definitive proof of the wave nature of light came in 1801 when Thomas Young did his double slit experiment. Okay. So what he did was, using a simple playing card, he was able to demonstrate that sunlight through a single slit did diffract around the card, and then he later performed the experiment with two slits to demonstrate that diffraction from both the slits produced interference patterns that formed alternating region of bright lines. Okay, so he got light to diffract and interfere, which is a wave property, which made scientists say that, okay, maybe light is a wave. Okay, so double slit diffraction looks like this. So if we have one opening and you send light through, it'll bend around the corners like that. And these lines, they represent the crests of the wave. So it's sort of like, if this was our wave, that would be a line, that would be a line, that would be a line there. And if you send it through another opening, right, it would diffract around the corners like that. So if you put these openings close enough together, what you end up getting is you end up getting these lines to cross over like that. And remember, these lines represent crests. So this is a crest, 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 this is a crest. So these are where crests are matching up, are these points that I'm highlighting here. So these are where crest matches with crest, and where crest matches with crest, you get constructive interference. So what we get is we see that right down the middle here, we get crest matching with crest, and we get a nice bright line. We'd get that again here, and we get that again here. I think I drew that wrong. Sorry, the next one would be here. So we get bright lines here, we get bright line here, right? We get these bright lines that would show up, and in between these bright lines, you can see that this line zigzags back and forth, and that zigzag is where crest meets with trough. So this would be the zigzag where crest is meeting with trough. So we'd get dark lines, dark lines, dark lines, dark lines in between, right? So this line right down the middle is an important line. This is called our central maximum. So that's our central maximum. And then we get a dark line, bright line, dark line, bright line. And that's what Young's double slit experiment is. Okay, so here's another picture of it where you have a light source. You have a screen with two openings through it. That light diffracts. We get constructive, destructive, constructive, destructive, constructive, destructive as it goes through. And we get these areas of bright lines and these areas of dark lines. Okay, this is what the experiment looked like. So I can show you, I'm just going to go grab diffraction grating. I can show you what this looks like with just a laser pointer and a diffraction grating. So let me just grab it. Give me 1 second. This is vamping a little bit. I forgot to grab this before. I found a diffraction grating. And found a laser. Good. Still here. Sorry, my laser didn't work. All the batteries are dead in the lasers. There we go. Okay. Okay, I'm coming back. Sorry for the time delay. Just skip ahead the video. Okay. So I can show you diffraction. Just going to shut off my lights here. So here I have a laser pointer, and this laser pointer just has one beam of light. This you can't really see is a diffraction grating. I'll light it up a little bit. It's a diffraction grating so you can see. And I send the light through the diffraction grating, and this is what we get. We get these areas of bright lines and these areas of dark lines. And depending on how close together the lines are, we get different interference patterns, right? So you can see we get a lot more dots here, we get less dots and less dots here. So this is the experiment that Young did. Okay. So what you need to do the experiment is you need two slits, and the distance between the slits we call D. And then the length of the screen, so I was just projecting on the whiteboard on my desk there. So this is from the slits to the screen. That's what we call L. And then what you get is you get areas of brightness and then areas of darkness. So this is my bright line, this is my bright line, this is my bright line. The bright line right down the middle, like I said before, is called the central maximum. And then we call this n equals 1, and we call this n equals 2. And it's always symmetrical on both sides, so this is n equals 1 as well. And then this is n equals 2 as well. And then the distance in between this, the distance in between the brights, we call x. And it's a little bit confusing because there's three distances in the formula. There's x, which is the distance between our bright lines. There's L, which is the distance to our screen. And then there's D, which is the distance between our slits. And the way that I remember it is really stupid. But whenever I say D, I always say the dist between our slits. That's what plays in my head as I do it. I say dist between the slits. And that's how I remember D is a dist between the slits. And if I say that enough, you'll remember it, kind of like Y sine, if you remember that. Dist between the slits. Okay, so these are our two formulas, where lambda is wavelength, D is a dist between the slits, L is the length of the screen, N is the order of bright fringe, theta is the angle from the central maximum, X is the distance between bright or dark spots. And this little bullet says that the first equation relies on an approximation. It is assumed that X is very small compared to L. This only works with angles of less than 10 degrees. Okay, so what that means is if you have, I draw a triangle, and this is L, this is the length to our, this is our slits, this is our screen here. And I want to go smaller. And you have an angle that's really small here. So this is my angle right here. If we make a triangle with this is a 90-degree angle. If our angle is really small, this line here and this line here will pretty much be the same length, right? But if we get an angle that's much bigger, right? This is 90-degree angles, and this is a much bigger angle. Well, now this one is our hypotenuse. This one's a lot bigger than this. And that first equation doesn't work for a situation like that. It relies on this line and this line being relatively the same distance. So that's what that small approximation rule is. So we have to do a little check before we do questions with this. Okay. So let's do some examples. Okay. So light falls on a pair of slits 1.35 micrometers apart. The maxima are measured to be 41 centimeters apart, and the screen is a distance of 1 meter from the slits. Determine the wavelength of the light using each of the equations. Okay. So we're going to do this with both. Oh, you can find these formulas under waves. They're the last two. They're these two right here under waves. So I find it helps to draw out the experiment a little bit. So here is our slits. So here we have two slits. So remember that this is D, that's the distance between our slits. Here's our screen over here. So this is L, and then we produce these bright dots. This is my central maximum. This is 1, this is 2. Sorry, this is 1, and this is 1, and this is 2, and this is 2, and this is X right here. Okay, and let's draw on what's happening. So it says that the slits are 1.35 micrometers apart. So 1.35, and micro is times 10 to the 6. So 1.35 times 10 to the 6 micrometers apart. The maxima, and the word maxima just means the bright lines. So the bright dots are measured to be 41 centimeters apart. So 41 and centa is times 10 to the negative 2 meters. And it says the distance for L is 1 meter. So just make sure they're all in meters. Determine the wavelength using both of the equations. Okay, so if we use lambda equals xt over nl, our first equation, we can just plug this in. So x is 41 times 10 to the negative 2 meters. The distance between the slits is 1.35 times 10 to the 6 meters. We're just going to measure to the first bright spot, so n is going to be 1, and then the length is 1 as well. We end up getting 41 times 10 to the negative 2 times 1.35 times 10 to the negative 6. So we end up getting 5.535 times 10 to the negative 7 meters. And when answering wavelengths of light, the answer on a test is going to be in nanometers a lot. So we want to move it over 2 spots. So it's times 10 to the negative 9. So this would be 554 times 10 to the negative 9 meters. Okay. So if I gave this answer, this would actually be the wrong answer on a test because we didn't check our angle. And I think this angle ends up being too big. So if we want to use the other formula, we're going to use lambda equals, let me use this formula, d sine theta over n. If we want to use this formula here, what we need to do is we need to find this angle. Okay, so the angle, so this is L, which is our length right here. And then we know that this is 1 meter. And this is our bright spot. This is our central maximum. So we know that this distance is 41 times 10 to the negative 2 meters. So if we have 2 sides of a triangle, we can find our angle, right? This is opposite. This is adjacent. So all we have to do is tan negative 1 of opposite, 41 times 10 to the negative 2, over adjacent, which is 1 meter. And we end up getting our theta is equal to 22.29 degrees. Okay, so if our angle is more than 10, we can't use this formula, and you'll see why when I plug this in. So the distance between our slits is 1.35 times 10 to the negative 6 meters. And then we have to sign that 22.29. I'm going to use my whole number, and we're just measuring to the first one. And when we do that, so sine of my answer times 1.35 times 10 to the negative 6, we end up getting 5.12 times 10 to the negative 7, or 512 nanometers. Right, so you can see these answers are quite different, and that's because the angle is so big. If that angle was smaller, then we wouldn't see the difference between them. They'd end up being the same. So this would be the correct answer. This would be the wrong answer on the test. So you always got to check your angle to see if it works. Okay, so let's do another question. No, we don't do another question quite yet. So these days, instead of two slits, diffraction gratings are used, where upwards of millions of lines per meters are etched into glass. This is how CDs work. CDs, if you know what compact discs are, they're diffraction grating, and the computer sends laser light, and it diffracts through the CD, and that the way it diffracts is information based on the etchings of lines per meter. So CDs are just big diffraction gratings. So the distance between the slits is exactly the inverse of the number of lines per meter. So what that means is that lots of times diffraction gratings are given as 100,000 lines per meter. Then the distance between the slits is just the inverse of that. So we 1 over that, and that would be, I'll write it out. So if we have 100,000 lines per meter, we don't want our answer in lines per meter. We want meter, how many meters are in between each line. So what we would do is we just flip it. 1 meter per 10,000 lines, right? And then you have meters per line, and that's what we want. So you just have to inverse it. So we'll do a question that shows that. So the spacing between two slits is 200,000 lines per millimeter in a Young's double experiment. It should say the spacing. This question is flawed. Spacing of diffraction grating is 200 lines per millimeter in a Young's double slit experiment. The distance from the slits to the screen is 1 meter again, and the distance from the central maximum to the second bright spot, the second maxima, is 22 centimeters. Determine the wavelength of the incident light used in the experiment. Okay, so we got quite a bit to do before we actually do this question. So let's keep our drawing from before. Okay, I don't know why this is showing up. Let me just go away. Oh, no. Sorry, the things are just showing up on the side and usually they disappear. Well, it disappeared for a sec. Now, whatever. There it goes. Now it disappeared. Camera moved a little bit. There we go. Okay, so first thing we need to find out is the distance between these slits. And we should be in meters because other stuff is given in meters, because this is given in meters. So it says that we have 200 lines per millimeter. That's what it's given as. So we need to switch this into meters first. So there are 1,000 millimeters in 1 meter. And you can look that up on your data booklet, right? Because it tells us on a data booklet back to the beginning of the semester. It says here a millimeter equals 10 to the negative 3 meters, or you can just memorize 1,000 millimeters in 1 meter. But you could also use this as well, but you got to make that conversion. Okay, so that would cancel out our millimeters. So that's lines per meter, and then we inverse it to get meters per line. So if I go 200 times 1,000, and then I inverse that, we get 5 times 10 to the negative 6 meters in between the lines. And that's what we want it to be in 5. This is 5 times 10 to the 6. Sorry, there's a little bit of a glare there from my lights. Okay, so this is going to be 5 times 10 to the negative 6 meters. Okay, the question also says that to the second maxima is 22 centimeters. So this distance from central maximum to our second one is 22 centimeters. And we want to determine the wavelength of the light. So very first thing we're going to do is we're going to check to see if our angle is less than 10 degrees. We want to find this. So this is 22 centimeters. This is 5 times 10 to the negative, oh sorry, this is 1 meter. That's the length of the screen. So if I go tan negative 1 of 22 over 1, I end up getting, sorry, this is in centimeters. There should be 0.22 meters. Sorry, so I go tan negative 1 of 0.22 over 1, and I end up getting 12.407 degrees. Okay, so that means that I can't use that first formula. I have to use this one. And I want to find my wavelength, so my distance between my slits is 5 times 10 to the negative 6 meters. Sine of 12.407. I'll use my full answer. And we are finding to the second maximum, so that bottom number has to be 2. So we sine our answer, multiply it by 5 times 10 to the negative 6, and divide it by 2. And we end up getting 5.37 times 10 to the negative 7 meters, or 537 nanometers as our answer. Okay. So, next question is a board question. So you can pause the video, try it yourself. I'll go through it too. I think it's good to have one more practice at this. So pause that video. I'll go through it. So 400 nanometer violet light from a laser pointer is pointed at a diffraction grating screen. Is placed 2 meters away. The first dark spot. Ooh, this is tricky. Okay, so that's our screen. This is our L. This is our slits right here. So this is D. And we're trying to find D. And then this is our central maximum. This is our first bright spot. So we're actually finding to the first dark spot. And it says that the first dark spot is found 21.3 centimeters away. So if this is 0, essentially, this is 1, then our first dark spot is going to be 0.5, right? Our next dark spot is 1.5. So the dark spots are all 0.5s, which is a little bit weird. It says their screen is 2 meters away, and we're using violet light. Okay, so first thing we're going to do, check our angle. So this is 2 meters, and then 0.213 meters to our first dark spot. So I tan negative 1, opposite over adjacent, and I get our angle to be 6.07 degrees. So that means we're free to use that first formula, and I will use it. So if I use that first formula, lambda equals xd over nl. We want to find our distance between our slits, so we move nl up top and x down below. So n is going to be our first dark spot, which is 0.5. Length to our screen is 2 meters. Lambda is 400 nanometers, so 400 times 10 to the negative 9 meters. And then the distance for x is going to be 0.213 meters. So I'll plug all of that into the calculator. So we end up getting 1.8779 times 10 to the negative 6 meters between lines. So it wants us to give our answer in lines per millimeter. So we'd have to switch this to millimeters. So meters down here, millimeters up top. Would cancel that out. So there's 1,000 millimeters in 1 meter. And then we just have to inverse it to switch it around, because now we're millimeters per line. We want lines per millimeter. So I take my answer, multiply it by 1,000, and inverse it, and I get 532.5 lines per millimeter as my answer. Okay. Okay, so hopefully that worked out okay. So last thing we're going to do is we're going to talk about prisms and diffraction gratings. So we know that prisms break up white light into all the different colors because the different wavelengths refract different amounts, right? That's Snell's law. That's what we did in the first test. So using Snell's law, we know that red light refracts the least because the inverse relationship between the index of refraction and wavelengths. So when we send white light through, we get, remember, red refracts the worst. That's an R. Red refracts the worst. And then that means blue or violet light is going to refract the best. So when we talk about diffraction, according to our new formula, the diffraction gratings are able to break up white light into its colors. So we see that the wavelength and the angle that it diffracts it are a direct relationship. So if we increase the wavelength, we increase the angle. So if we increase our wavelength, what will happen to our angle? Well, it's going to be bigger angle. So that means that diffraction gratings are the opposite. Red is 700 nanometers. So that's our biggest wavelength. And that's going to have our biggest angle. So red is going to diffract the best. And then we get blue or violet is going to be the worst because it's the smallest wavelength. And we always get it the same on both sides. So it's always symmetrical with diffraction gratings. We get red to do the best, and then blue is the worst. So it's opposite. So you have to memorize that it's opposite. Okay, so this is your homework on double slit diffraction, and there's a graphing question there. And we're going to do a lab related to that graphing question as well. Hopefully this goes okay. Email me if you have questions, and I'll go over the sample diploma questions tomorrow because this is already a 40-minute lesson. So, yeah. So I wanted to go through these sample diploma questions before you write your quiz tomorrow. So let's go through these sample diploma questions. So in an investigation, a group of students directs light from a laser pointer at a diffraction grating that has a line spacing of 1 × 10 to the -5. A series of bright lines appears on the screen, placed 1 meter away. The student measures the distance 5.56 between the central bright spot and the first order. So based on the student's measurements, the wavelength of the light emitted by the laser pointer is cool. So let's do this. So the very first thing you have to do with any of these questions, so this is our L, which is 1 meter, and central bright spot to our first bright spot is 5.56, so 0.0556 meters. So you have to find your angle, right? Or else you can't use that formula that it doesn't work for. So you have to tan -1 opposite over adjacent. And you get your angle to be 3.18 degrees. So that means that you can use any formula you want. You can use lambda equals xt over nl, or you can use lambda equals d sine theta over n, right? So they do want to know the wavelength. So I'll show you how you get the same thing using either formula for this one. They might be slightly different, but both answers would be accepted. So 0.0556. And your distance between your slits is 1 × 10 to the -5 meters. It's the first bright spot, and then they're 1 meter apart. So if I do it like this, so I get 5.576 × 10 to the -7 would be my answer. And then if I use this one, 1 × 10 to the -5 meters, sine of my 3.18 degrees, all over 1. answer times 1 times 10 to the negative 5, and I get 5.55 times 10 to the negative 7 meters. Right, so both of those answers would be accepted, so I would accept 5567 and 5557 as the answer because it's under that 10 degrees. But with this next question, in an investigation, same thing, different line spacing, different measurement, first order bright spot, and we want to find the wavelength, right? So it's the same idea with this one, but only our distance is bigger. So instead of our distance being 556, it's 0.439 meters. So if we do, oh, it's still 1 meter. Yeah, still 1 meter. So 0.439 meters. So when I tan -1 that, I get 23.70 degrees. Right, so now I don't have both options. I have to use this one here. And I'll show you how different the answers are when we do it both ways. So my line spacing is 1.67 times 10 to the negative 6 meters. And then 23.7, I use my full answer for that. So I sign my answer times 1.67 times 10 to the negative 6. And I get my answer to be 6.71 times 10 to the negative 7. So this would be the wavelength that is accepted. But if you tried it using this one here, so my x is 0.439, and my distance between the slits is 1.67 times 10 to the negative 6 meters. We get 7.33 times 10 to the negative 7 meters. So this is not the answer. This would be marked wrong because your angle is greater than 10 degrees. Okay. If it's less than 10 degrees, you can use either, but if it's greater than 10 degrees, this is the only one that you can use. So it's really important that you check that angle every time you do the question. Okay, in a double slit experiment, a screen is 2 meters from the double slit, and the wavelength of light is that. What slit separation would produce a second order fringe from the central bright spot? Okay, same idea. So in doing this one, because we're trying to find the angle, or we're trying to find, we were trying to find D, so we can check, right? So our L equals 2 meters, and then we find the second order bright spot is 1 times 10 to the negative 2 meters. So if we check that, we tan -1 opposite over adjacent, we get our angle to be 0.28647 degrees. So we can use either formula, and we're going to get the exact same answer because that, oh, sorry, I'm not on the right screen. Sorry. We'll get the exact same answer no matter what when we do, because that angle is so small. And the smaller the angle, the more close our answers are going to be. Okay, so we're trying to find our slit separation. So again, let's use lambda equals xd over nl, and we're trying to find d. So we move nl up top and x down below. So it's a second order, so we have to put 2 in there. The length to our screen is 2 meters. Our wavelength is 5 times 10 to the negative 7 meters. And then 1 times 10 to the negative 2 meters is our x. So we plug all this in, 2 times 2 times 5 times 10 to the negative 7. And then divided by 1 times 10 to the negative 2. And we get 2 times 10 to the negative 4 meters is our slit separation. So it looks like C is the correct answer. Okay, this one's a tricky one. You can see it's a standard of excellence question here. I'd be curious of what you guys would put as this answer. So students use a green laser pointer and an optical apparatus to produce an interference. So just like the lab that we did yesterday. The ruler is 50 centimeters from the optical apparatus, and the wavelength of the green laser is that. Students analyze the observations and calculate the distance between the openings. So I always get a little bit of everything for answers. So in order for the student's analysis to produce the most accurate, you can see this is bolded here, calculated value of the distance d between the adjacent openings. The students measure x and the distance from the central maximum to b, and the equation they use is blank. Okay. So each one of these answers is going to be correct, and it all depends what you use. So what a lot of students will use is they'll use the central maximum, which you should, and then this guy right here, which looks to be about 6.5-ish. Okay, that's what a lot of people will use. And then if you check your angle, let's switch our screens. So it says that it is, the ruler is 50 centimeters, so our length is 50 centimeters, and then to our first bright spot is about 6.5 centimeters. And as long as they're both centimeters, I can keep it in centimeters, it's fine. So I tend -1, 6.5 divided by 50, and I get my angle to be 7.4 degrees, right? So it's like, cool, we can use either formula. So if I use lambda equals xd over nl, and I try that, or I use lambda equals d sine theta over n, I should get the right answer, right? So we're trying to find, what are we trying to find? The distance from the central maximum to the we're trying to find d. So we move nl up top and x down below to find d. And so we're measuring to the first one. Our length is 0.5. For the formula, we have to switch it into meters. Our wavelength is green laser, so it's 557 nanometers, so 557 times 10 to the -9 meters. And then we measure 6.5. So if we plug all that in, this is going to be in meters. So divided by 0.065, so we get 4.28 times 10 to the -6 meters. And if we use this one, so we move n up top and sine theta down below, like that. So it's our first one. Our wavelength is 557 times 10 to the -9 meters, 557 nanometers, and then sine of our 7.4. And I'm going to use that full answer from before. Okay, so it's going to be 1 times 557 times 10 to the -9 divided by sine of our old answer, and we get 4.32 times 10 to the -6 meters, right? And they're a little bit off, and that's what we saw in the last question, and it's like, okay, that's okay. So if we look at our answers, oh, we did this, and we got this as an answer, so this looks to be correct. And we did this and we got this as our answer, so this should be correct. So there's 2 correct answers here. And these are both actually wrong. And the reason why they're wrong is because it's asking for the most accurate answer. So remember that whenever you're measuring something, the bigger the distance, the more accurate it's going to be, right? Because if you have you can see it's a little bit foggy in here. And if we have a little bit of human error in here, and if we have a little bit of human error in 6.5 centimeters, well, let's say we're plus minus 0.5 centimeters, that's a lot of error, right? That's like 10, 15% error, and that's not going to be accurate. But if instead we measure to our 1, 2, 3, fourth line here, right, and this looks to be about 28.7 centimeters, and we're still off plus minus 0.5 centimeters, well, we're going to be a lot more accurate with this. So the reason that these are wrong is because it's not as accurate. And if we're measuring this far out, our angle is going to be way bigger than 10 degrees because this one was already at 7 degrees. So we need to use this formula, which makes this the correct answer. And you actually don't even need to calculate anything for that. You are going to get this answer if you plug in that. But this is the most accurate answer. So D is the only correct answer for this one. Okay, and this last one, classic one, is asking you to compare a prism and a diffraction grating. So remember, with a prism, red refracts worst. It refracts the worst. So red is going to be here, and blue or purple or violet or whatever you want to call it. It's all the same in physics. Blue, purple, violet, all the same. So we have red and we have blue. It's going to be like that. And I always remember that diffraction gratings are opposite. So red is going to diffract the best, and blue is going to diffract the least, right? Same thing over here. Red is going to refract the best, blue is going to diffract the worst. So at P, we're going to have blue, and then at R, we're going to have red. So D is the correct answer. Okay, those are the kind of questions I'll be asking you on your quiz tomorrow. So hopefully that went okay. And yeah, I'll post that quiz tomorrow, and you guys have a couple days to do it. So.